Let's take a look at this orthogonal projection. Orthogonal projection of a vector onto a vector is given by this formula. Projection of v onto u. And the formula says that we take the inner product of v and u, and then that's going to be the scalar that we're going to multiply u by. Now u is a unit vector in v. And if u was not a unit vector, our formula might look a little bit different. So I want to put a little recall here from your usual dot product definition of the inner product, that the projection of v onto u, if u was not necessarily a unit vector, is going to be v dotted with u, and we're projecting onto v. So the scalar projection is going to be this dot product of v and u divided by the magnitude of u, but then you're going to multiply by u, but you have to make u into a unit vector, so you'll have another magnitude of u in the denominator, and so this becomes your projection formula. Now geometrically, what we see, if you remember, is that a u vector, whether it's a unit vector or not, and then there's a v vector. So this is your v vector, and your unit vector here is just a vector, but we really can look at it as the span or a line. And then the projection is going to be an orthogonal or perpendicular projection of v onto that line. And so the vector that we get this vector in red here is the orthogonal projection of v onto u. Okay. Now it turns out that since this is an orthogonal projection, we can actually subtract v minus u, or v minus this projection vector that we just got, and then we're going to get another vector. So that other vector turns out to be another important vector for us. And so that other vector that's important to us is orthogonal to u. Not just orthogonal to u, but it's actually orthogonal to the whole subspace spanned by u. And I think that is going to be the important generalization that we're going to examine. So this vector here we're calling orth of v onto u is really just a difference between the v vector and the orthogonal or the projection vector that we just found. So it's parallel to u, it's within that space, and the projection vector is parallel to u, but the orthogonal vector is perpendicular to u. Okay, so here's a quick summary. The projection of v onto u is within the span of u. Orthogonal vector v onto u is perpendicular to the span, and if you add the projection and the orthogonal vector, it's essentially that v vector that we're looking at. So that part's not so important. I think what is important is this property here, that the orthogonal vector is perpendicular to the span. Alright, now we can generalize this into subspaces. Orthogonal projection of a unit vector can be looked at projecting this vector v onto a span. So let's just say we have u. Let's just keep it to two vectors. So say we had two vectors, u1 and u2. And because there's only two vectors here, and assuming they're linearly independent, we can say that they actually span a plane. Now, if there's another vector v, let's say there's another vector v that's not on the plane. So there's some sort of angle there that it's going out of the plane. Then we can find the projection vector of v onto our subspace. And what that turns out to be is that we drop a perpendicular onto the plane, and then we're going to get this other vector that's on the plane. And that vector is called the projection of v onto the subspace U. This should just be a subspace, capital U. And again, we're talking about U as a span of U1 and U2 vectors. So that's the projection. Now, if we do the subtraction, the same subtraction that we did, then we will get ourselves a vector that is perpendicular to the plane. So that vector that's perpendicular to the plane will be labeled orth of v onto the subspace U, and that is going to be given by the difference of the vector v and the projection vector u. So this vector is orthogonal to u, and again we summarize. The projection vector itself is on the plane. It's within the span of all those vectors. The orth vector is orthogonal to u, and then sometimes we can say it's in the perp, u perp, and then v is equal to the projection plus the orthogonal vector. So again, it's the second property that's going to be most important for us. And that brings us to the Gram-Schmidt orthogonalization process. The idea behind this process is to take a look at a set of vectors that form a basis to a particular space. And what we want to do is we want to create, so this process will help us create an orthonormal basis. So it really just takes a few steps, depending on how many vectors you are, or how many vectors you have. So our first step is to normalize the vector, the first vector v1, and that's going to go in our set. So we're going to collect a bunch of normal or unit vectors that we're going to build our set from. When we start with v1, we normalize it, and then now we have one vector in our set. Now we take V2 and project V2 onto V1. It's the same as projecting it onto U1. And then we get our projection vector, and we find our orthogonal vector. And we're going to temporarily call that W2 because this vector is going to be orthogonal to the first vector, but it may not necessarily be a unit vector. And so as our last step, we make it into a unit vector. And then now we have two vectors, U1 and U2, that are orthonormal. So we'll continue on. We take the span of that, and then we're going to project our third vector, V3, onto the span of the other two vectors that we found. So we use our projection formula for that, and then we find our normal vector to that. And then this vector may or may not be of unit length, and so we just divide by a unit vector or divide by its magnitude, and then now we have 3. So we keep going in this process, and our process will involve a longer and longer formula based on a projection, and then we'll take that value of projection and subtract it from the vector that we're currently dealing with, and then we're going to get our orthogonal vector, and then we normalize it, and then now we have we added another one to our set. So we're going to keep doing this until we complete our basis. Alright, so that's the process, and we will take a look at a few examples.